So here we have problem 3.28, and I've taken the liberty of writing down equation 3.95 from the book, and that's what we'll be using to solve this problem. Before we can begin plugging things in, we have to figure out the rho d tau term and the cosine alpha. So for rho d tau, this is just going to be lambda dl prime, but the dl element, if you look here, we're always going to be at radius r, so the r is not going to change, and then the what we'll be doing is rotating by phi prime, so really it's just going to be lambda big R d phi prime. So that covers this part, and now for the cosine alpha. Alpha is the angle between the r and r prime vectors. So first it'd be good to define what these vectors are. So for r, this just points to some xyz, and we're in spherical, so you can recall the definition of x, y, and z in spherical, and we'll get this right here. Actually, let me zoom in. There we go. So that's our r vector, and for r prime, we also want to define that. Observe that r prime exists in the xy plane, so no z component, it's just a two-dimensional, it points to something in 2 dimensions. So here we see that there is only an x and y component. Alright, and then from this we can recall the definition of the dot product of vectors, and so we can dot these two, and we'll get their magnitudes times the angle, cosine of the angle between them, right? And so we'll just go ahead and dot these two things. Which will give us I'd like to, I guess I can pull out the sine theta later, but they'll both have a sine theta here. Okay, so we can divide by little r big R to get the cosine alpha on its own, and we'll see that these will cancel, and so we'll be left simply with this here is the cosine alpha we were looking for. So now we can plug this here once we actually start working with trying to find the terms. And with this we have everything we need to get started. So I'll just take this equation and copy it over here. And so let's begin with n equals 0. And so what we're going to get is, and I'll just do the sum, and then I'll multiply the 1 over 4 pi epsilon naught. Shouldn't say equals. So, alright, for n equals 0, we'll have r to the 0 plus 1, and then here we'll have r prime to 0, and the Legendre polynomial will be the 0th, and of course for here we have our lambda r d phi. And r prime to the 0 is just 1. The 0th Legendre polynomial is just 1. So really we just have to worry about this d phi prime. And what we're doing here is we're doing a full rotation with phi prime. So this is going to be from 0 to 2 pi, and this will be the case for each of the terms that we're looking for. So okay, this is just an integration of d phi, and these are just constants that get pulled out to the front. So this one's pretty easy, and we'll just end up with lambda r over 2 epsilon naught r. Once we multiply by 4 pi epsilon, 1 over 4 pi epsilon naught. So because the 2 pi's cancel, and this is going to be our first term. So now we just repeat that same thing for n equals 1. So now it's going to be 1 over r to the 1 plus 1, so r squared. This time r prime is to the first power, so it does it will exist this time around. And the Legendre polynomial is going to also be the first term. So in this case, the first Legendre polynomial is just going to be cosine alpha. And as for r prime, the magnitude of r prime is just the radius. So a big R goes here. So then it's just lambda, another big R, d phi prime. So we can pull out the constants. And we'll get big R squared lambda over R squared, the integral from 0 to 2 pi. And now we'll have a cosine alpha here. And we're integrating in terms of phi prime. So we take our definition and we plug that in. So we figured out that this is what cosine alpha is. And like I said before, we can pull out a sine theta to make it a little bit nicer looking. And so this is what we plug in for cosine alpha. So, whoops. Now we can actually integrate this. And you'll see that although there are a few trig functions, the only ones that we care about are cosine and sine of phi prime. So it's just the integral of cosine and integral of sine, and then we plug in our limits once we integrate. So that amounts to, once we've actually integrated, we'll end up with cosine phi sine phi prime minus sine phi cosine phi prime times sine theta that we pulled out. And here are our limits of integration. Observe that 2 pi and 0, sine of 2 pi and 0 is always going to be 0. Cosine, it's going to be 1. So we're going to end up with a situation here where we get 0, 0 minus 1 minus 0 plus 1. So this is actually all going to cancel and go to 0, which means that this term is just 0. So our second term is just 0. Now, the final term, the third term, we're going to plug in 2. So we'll get 1 over r to the third, 0 to 2 pi. And now r prime is squared, so we'll have a big R squared. And for the Legendre polynomial, we're going to have the second order Legendre polynomial, which is this right here. This, or 3 cosine squared minus 1 times 1/2. So this is going to complicate things a little. Because I almost forgot this part. Because here we have a cosine squared alpha. What that means is that this right here is now getting squared. So we take this and we square it. It becomes a little tedious, but this is, at the end of the day, just algebra. So we'll square this and get a huge expression that's going to end up being this. Please excuse me while I write this thing down. All of this d phi prime. Now I'm just putting it into the integral. Might as well. And in the front, you know, you can pull out the constants. So the we're going to have an r cubed lambda. So over 2r to the third. Again, here I just pulled out the 1/2 from here to get the 3 cosine. Or I mean the, well yeah, 3 cosine minus 1, which turned into this thing. So here is what we have to integrate. It looks huge, but again, all we care about is this term, these, this, and this one. So the one is just d phi prime. Then for the cosine squared and sine squared, we can use the half angle identities. And then for sine and cosine, just a simple u substitution will work. So once we integrate those, we'll end up getting that this right here goes to pi. This becomes 0, and then this also goes to pi. And well, obviously this is just going to be 2 pi. We know because the previous integral had that as well. So with that, we can now write this again in a much more, hopefully neat fashion, because we'll have this in front, and then we'll have cosine phi times the pi we got plus 0 plus sine squared phi, the pi we got, and then minus 2 pi. So observe that this is just 1 cosine squared plus sine squared. So this is just 1 times pi, and that ends up just being pi. So we're going to end up with pi for this whole thing, And we can pull out a pi because it's 1 here, and now what we're left with is 3 sine squared theta minus 2. Now, if we want to simplify this further, this is just 1 minus cosine squared theta. And in doing that, we're able to get 1 minus 3 cosine theta. And if we were to pull out a negative sign, we'd get negative of what we had before. And sorry, I forgot the 2. Here we can actually pull out, or sorry, rather reincorporate the 1/2. And notice that if we do that, this is just the second order Legendre polynomial, P2, of cosine theta. And so here in this more simplified version of the answer, it'll be this times P2. And remember that we have to also multiply it by the 1 over 4 pi epsilon naught from the beginning, because this was just the summation part. And so what we end up getting once we multiply that is we'll end up with this right here. And this is the final answer for the second term.